Hi, in this tutorial we have an exercise related to Newman projections of butanes. The question in the exercise asks us cite down the C2-C3 bond and draw Newman projection of the most stable and the least stable conformations of 2,3-dimethylbutane. In order to solve this question, we have to draw skeletal structure of 2,3-dimethylbutane. So in butane we have 4 carbons, and in the second carbon we have a methyl, and in the third carbon we have another methyl group. And let's show the numbering of carbons. Then we have to cite this molecule through second and third carbon. So there should be here an observer looking through this second and third carbon. And when this observer looks at through second and third carbon, the second carbon will be the front carbon and the third carbon will be the back carbon of the Newman projection. So the back carbon is shown with the circle, and the front carbon will be shown with the dot in the center. So in the front carbon, in the second carbon, we have methyl, methyl, and a hydrogen attached. So randomly, I will place 2 methyl groups and 1 hydrogen. When we look at the third carbon, we have also here 2 methyl groups and a hydrogen attached to the third carbon. So again, I will randomly place 2 methyl groups and 1 hydrogen coming from the back carbon in the Newman projection, and I used staggered conformer because we know that staggered conformers are more stable than eclipse conformers. So this might be the most stable conformer, but we have to check. When we look at the Newman projection, we can see that we have 3 methyl-methyl gauche interactions. Let's write here 3 methyl-methyl gauche interactions. These are steric strains. These causes steric strains, and it might be the most stable conformer, or it might be a less stable staggered conformer. We have to check other staggered conformers. So how are we going to check other staggered conformers? The strategy is generally rotating either front or back carbon 120 degree so that we can end up with another staggered conformer. So how are we going to rotate the back carbon 120 degree? I prefer generally rotating back carbon clockwise 120 degrees. So the back groups attached to number 3 will rotate 120 degree so that we can end up with another staggered conformer. So these groups will change their places and we will end up with another staggered conformer. So let's draw that staggered conformer. Again, we have to draw a circle for the back carbon number 3, and we have to place a dot for the front carbon number 2. So the front carbon was kept stationary. We didn't rotate it, so all the groups should preserve their places, but the back carbons group should move 120 degree clockwise. So this methyl group will move in place of that methyl group, and this methyl group will move in place of this hydrogen, and this hydrogen will move in place of this methyl group. So we ended up with a different staggered conformer. Let's analyze the interactions. Here we have methyl-methyl gauche interaction, and here we have another methyl-methyl gauche interaction, and in total we have two methyl-methyl gauche interaction. So the first one had three gauche interactions. The second one has two. So for that reason, the first conformer has more strain. For that reason, it is less stable as compared to the second staggered conformer. Let's write here, this has less strain, and for that reason it is more stable. So now we ended up with the most stable staggered conformer. Now we have to draw the least stable conformer of 2,3-dimethylbutane. We know that eclipse conformers are generally least stable conformers. So let's draw here a template for eclipse conformer. Okay, so this is the front one. Again, I will keep the front one as it is. So we have a methyl, another methyl here, and hydrogen. And if you look at again the third carbon, we have two methyl groups and one hydrogen. So I will here put eclipsed groups behind these groups, and they will have eclipse interactions. They are eclipsing each other. So I prefer for the least stable one, two methyl groups should be eclipsed by the other two methyl groups, and hydrogen should be eclipsed with the hydrogen. We know that when we have eclipsing interactions, we have torsional strain. In addition to torsional strain, if we have bulkier methyl or other groups, we can have also steric strain. So here we have two methyl-methyl eclipsing interaction. We might have another eclipsed conformer, but it may not be the least stable one. Again, I'm going to keep the front same, and for the back I'm going to rotate everything 120 degrees, so this methyl can come in place of this hydrogen, and this hydrogen can come in place of this methyl, and this methyl can replace this methyl group. So again, like, let's draw the methyl. So behind this hydrogen I will have another methyl, and behind this methyl I will have a hydrogen. So when I look at here, I will have different interactions. So in the first one I have two methyl-methyl eclipsing interaction and a hydrogen eclipsing interaction. But in the other one I have methyl-methyl, one interaction, one eclipsing methyl-methyl interaction, and I have two methyl hydrogen eclipsing interaction. And we know that when bulkier groups are back to back or eclipsing each other, they causes more strain. So this is basically, this has more energy, more strain, and it is less stable. So this one has less strain with respect to the other eclipse conformer, so it should be more stable eclipse one. So this conformer is the least stable eclipsed conformer. Thank you so much for watching the video.